Okay, attendance sheet is going around. Today we will be finishing up derivatives in electric circuits, and we will be starting derivatives in strength and materials, and we will finish up that material on Thursday, and that will be the last of the new material for exam number 2, which also means that by the end of the week I will post 3 previously given and solved exam number 2s. Okay, so you'll have a sense of what you're in store for. Okay, so we are moving right along. So, last time, I believe we left off talking about derivatives in capacitors. Okay, and so we'll do another example from EE 2010. Okay, and so let's say that we have a capacitor. Okay, and let's see, I've got plus or minus a voltage V of t across the capacitor, okay, and a current I of t that can flow through the capacitor, and it's got a capacitance C. Okay, and last time we talked about that the current I of t, okay, is equal to C times dV dt. Okay, that is the governing law. Okay, so the problem I'd like to work now is given a certain voltage, see whether or not we can find the current. Okay, so let's find the current I of t, okay, given the following. Voltage is 20 e to the minus 500 t, okay, multiplied by sine of 5,000 pi t. Okay, so there it is, and that is in volts. Okay, and let's say that the C, the capacitor, is equal to 25 microfarads. What's a microfarad, by the way? 10 to the minus 6, right? So this is times 10 to the minus 6 farads. Okay, that's the idea. All right, so I of t, according to this, is C dV dt. So I of t is going to be C, right, times dV dt. So we're going to take 25 times 10 to the minus 6, that's the capacitance, okay, times the derivative of this guy, dV dt. So we're going to need to take the derivative of that function. Okay, so I need dV dt, which is the derivative with respect to time of that guy up there. So we'll write it as ddt of 20 e to the minus 500 t times the sine of 5,000 pi t. All right, so going to need some help taking this derivative. What do you think? Do I have on the sheet, all right, if you haven't had calculus before, you should be getting pretty close to remembering what these derivatives are on the front side. Do I have this function on the sheet?
Well, there's the fx times gx derivative.
Okay.
There's whatever.
So.
There's the e and the sine wt formula.
Yep. So point is, I can find an e to the st on the sheet. I can find a sine omega t on the sheet. Okay, and so apparently what I've got is these two functions multiplied together. All right, so I want to think about this. This is another example of the product rule. What if the first part of this, 20 e to the minus 500 t, what if I think about that as some function f of t? All right, and I think about the sine of 5,000 pi t as another function, say, g of t. Then what I'm really doing is I'm taking the derivative of f times g. Right, and so if you guys recall, we have something called the product rule. Right, so I think we did one of these last time, but if I want the derivative with respect to time of f of t times g of t, what is that? First times the derivative of the second, so it's f of t dg dt, right, plus the second. Yeah, then I take the g and I multiply it by the derivative of the first, df dt. So you can do those in any order, right? First times derivative of the second, plus second times derivative of the first, or you can start with the second times the derivative of the first, right, and add the first times the derivative of the second. Either way. All right, well, if that's true, then apparently I got to do these derivatives with the product rule. So help me out here. dv dt. First function, 20 e to the minus 500t times the derivative, right, of g. So g is a sine 5,000 pi t. What would be the derivative? So the sine function gives me a cosine, right? This is a sine of omega t. So when I take that derivative, the omega is the 5,000 pi, right? So that comes out front. So first function, 20 e to the minus 500t times the derivative of the second. That's going to be the 5,000 pi, right, times derivative of the sine is the cosine 5,000 pi t. Great. That's the first term, first times derivative of the second, plus I have the second term times the derivative of the first. So this is plus, move on to the next line down here. Second term, sine 5,000 pi t times the derivative of this guy, 20 e to the minus 500t. Somebody want to take a crack at that? What's the derivative of 20 e to the minus 500t?
Well, the 20 is a constant, that's first thing.
Okay, great. So we'll put the 20 out front. Now I need a derivative of e to the minus 500t.
Negative 500 e to the negative 500t.
Yeah, so again, this is an e to the st. When I take the derivative of an e to the st, the s comes out front, and I get e to the st again, right? So the s in this case is the minus 500. So we'll have 20, right, times minus 500 e to the minus 500t, like that. All right, so I can kind of
Multiply that out.
multiply it out. Can I save a little writing here? See if I can't write this down in one step. Can I factor anything out of here? All right, so I got an e to the minus 500t in each of these terms, right? So clearly I can factor that out. What about some of these numbers? I got numbers here.
There's the 20.
All right, there's a 20 in each term. Any other number that can maybe be factored out?
Not really. Wait. The cosine. Nope, I'm not getting anywhere.
All right, so the e to the minus 500t can definitely come out front. It's in both terms, right? Can I take any numbers out that are common to both? We had the 20. Anything more than 20 that's common to both here?
No.
Yeah, what about 500? Right, I got 500 there. I got 500 times 10 here, right? Again, if this takes you more than one step, that's fine. But whenever I can, I try and do efficient algebra in here. Okay, so what I would do is factor out an e to the minus 500t. But out in front, what about 20 times 500? 20 times 500 is what? 10,000, right? So can I put 10,000 e to the minus 500t, right, out front? And if I have that, how much will I have left in the first term?
The 500 in there is negative.
In here it is.
Okay.
In here it's not. Okay, I could take the negative out if I want. If I did that, I'd have to put a negative in the first term. Right?
Okay.
So if I take 20 times 500, that's 10,000 out front. E to the minus 500t, how much is left here? I got 10, what else?
10 pi.
Pi. Okay, so I got 10 pi. So 10 pi cosine 5,000 pi t. Okay, and then I have another term here, which is plus, but you pointed out there's a negative there, right? So I should be able to put a minus sign there. And when I take out that 10,000 e to the minus 500t, do I have any numbers left in this term? That's it, right? 20 times 500 is 10,000. And here's the e, so all I have is a sine term. Sine 5,000 pi t. Okay. That's it right there. That's dV dt. Any questions on either one? The calculus, which is taking the derivative with the product rule, or the algebra that I did to go from this line to this line? Again, no problem at all if you want to do a couple steps of algebra to factor this out. But in the end, when you get a final answer, you want to simplify it as much as you can. So if you got numbers you can factor out, you probably ought to factor those out. Okay, the one other thing I could say, right, if I asked you, you know, what's the maximum value of this thing? Well, the maximum value of, right, the voltage, I would set that equal to 0. But the maximum value of the current, which is C dV dt, I probably would want to combine this sine and cosine, right? Sounds like a problem on the next exam. Sine and cosine, same frequency, magnitude, phase shift. I could do all of that stuff. I'm not going to do it here. We're just illustrating really the derivative in this case. Okay, but I have one more step, right, which is to get the I need C dV dt. So I of t is C dV dt. Right, and so I need to multiply by 25 times 10 to the minus 6. Okay, and so, right, this is 25 times 10 to the minus 6 times what we just got. So when I take 25 times 10 to the minus 6 and I multiply that by 10,000, what do I get? 10,000 is 10 to the what? 10 to what power is 10,000? It's 10 to the 4th, right? So this is 1 times 10 to the 4th. This is 25 times 10 to the minus 6. So I'm going to get what? 25 times 10 to the minus 2, right? Sorry, 2.5? Is that what I said it was? No, that's right. C dV dt. It's 25. Yeah, Josh has a typo in the notes, off by a decimal point. So it's 25 e minus 2, 0.25, right, times what's left over here. Okay, and so it's going to be, again, I got the 10 pi cosine times 5,000 pi t. Then I have minus a sine 5,000 pi t. All right, and that would be in what units? Oh, thank you. E to the minus 500t. So 0.25 e to the minus 500t. Yes. Okay, and the units on this would be what? Amps, right? Because I used base units for everything else. Okay, so this will come out in amps. Questions? Product rule, capacitor. Yeah, right, because look, this term is in front of all of this, right? So when I do a multiplication, once I multiply it, I'm done. Now I could take that and then, right, I could take this and I could distribute it into these if I wanted, but that is kind of unsimplifying it, right? I factored it out. Okay, so that's the idea. Other questions about that? I'll tell you guys, moving forward, when you take calculus, calculus profs will all tell you that the #1 reason for poor grades in calculus is algebra skills. Okay, and so that's why, like, feel free, anytime I'm working algebra, the more we move forward here, particularly when we get to differential equations, the calculus part of that pretty straightforward, but the solutions tend to be pretty involved, right? So you got to do a lot of lines of manipulation, algebra, trig, whatever. So getting the practice of being methodical and accurate in your algebra will really help your calculus grades, okay? So if you have questions about algebra and stuff as we go, please do not hesitate to ask. Okay, so last problem from electric circuits. Okay, let's look at a sketching type problem, okay, for a capacitor and using this idea of slope, right, in order to sketch a solution. Okay, so this will be current, voltage, and charge in a capacitor. Okay, so let's say that I've got a current source okay, applied to a capacitor like this. Okay, and so this is a capacitance C, and I'm going to have plus or minus a voltage across the capacitor that will result. Okay, and so this guy over here is the current source, I of t. Okay, let's say that the current, okay, is a series of constants. Okay, and we will go between 0 and 4 amps as follows, and actually it can be plus or minus. So this is 0 to 4, minus 2, minus 4, and I've got I of t over here in amps. Okay, on the y-axis, and on the x-axis, here's a part worth noting. This is time, but in electric circuits, time many times happens quickly. Okay, and so this time is in milliseconds. Okay, and so amps, right, up here, not milliamps, actual amps, okay, happening over milliseconds. So what we'll do is we'll go out for 5 milliseconds here, okay, and see what we get. So for the first millisecond, we're going to be at 4 amps. Okay, and then for the next second, we're going to jump straight down, go to minus 2 amps. Okay, by the way, what would a minus current mean in the context of this circuit? Just goes the other direction, right? So positive current flow, the way this is shown, would be in a clockwise, right? Negative just means it goes the other way. Okay, and then we'll hold it there for 1 millisecond, then we'll come straight back up, okay, and we'll stay at 2 amps, and we'll hold it there for 2 milliseconds, okay, and then we'll drop all the way back down to -4 down here. So we'll go straight down like that, hold it for the last millisecond, and come back to 0. Okay, and so again, this is 1, 2, 3, 4, 5 milliseconds on the x-axis. All right, so here's what I would like to do. Given our basic definition, okay, of current, voltage, charge, and a capacitor, I want to use that information to sketch some of this action. Okay, so, and actually the capacitor here, we know what it is. It's 20 microfarads. Okay, and so given this information, right, that I know by definition, I of t is the derivative of the charge dq dt, okay, which is the same across a capacitor as C dV dt. All right, so by definition, the definition of current is the flow of electric charge, right? So the rate, coulombs per second, okay, and it's the capacitance C times the derivative of the voltage. Okay, what I would like to do is sketch the stored charge and also the voltage. So let's sketch Q of t and V of t. Okay, that's what I want to do. All right, so is I of t the same value over all time? Nope. And do I have an equation for it? I mean, I don't have one equation for it over all time, right? And so whenever you have a problem like this that changes in each interval, you probably ought to want to look at it one interval at a time and see what you can conclude. All right, and so easiest way is we'll start with the Q. Okay, and by the way, in terms of a plan here, if we start by sketching Q of t, because I is just directly gives me the derivative, okay, once I have that plot, how will I get over here to voltage?
For time, is it milliseconds?
Yeah, milliseconds. Yep, ms is what that says. So once I have the charge, what'll be the strategy then to sketch the voltage?
Use the same thing except the multiplication of 20 UF.
All right, so it'll just be a constant factor here, right? So the plot's going to look basically the same, but we'll have to think about how the axis would scale because of that factor. Right? So that's the direction we're going. So we can get the action by really just thinking about the charge. Okay, and so we'll start with that. So starting with the charge, right, knowing that I of t, which is given, dq dt is the slope of I of t. Okay, what can we get in each interval? So for example, first interval, 0 less than or equal to t less than or equal to 1 millisecond. what's I of t equal to? Is I of t 0? 4. 4 amps, right? What kind of function is 4 amps? It's a constant function, right? So it's constant throughout the interval. It's not just that value at one point. It's over the whole interval, right? So it is 4. This is a constant, right? So if that's a constant, then that is the slope, right, of, sorry, Q, it's a typo here. The slope of Q is what I is. Okay, and so if I of t is the slope of Q, then what kind of function is a constant slope?
Linear.
Linear function, right? So this guy's constant. That means that Q of t is linear. So the conclusion, Q of t is linear. It's a line with a slope equal to what? Yeah, slope equal to 4. So if I think about what that plot would look like, assuming this thing is discharged at the beginning, right? It starts with a charge of 0. Okay, and so I've got a starting point of 0. Right, and it's got a slope of 4, so can I get the end point? Yeah. Sure. Right, so here's Q of t, right, and this is t over here in milliseconds. Okay, and I got to go out here 5 milliseconds. 1, 2, 3, 4, 5. So for 1 millisecond, I'm going to be linear with a slope of 4. Where's this thing going to end up after 1 millisecond? All right, so the slope of 4, I go over 1, I'm going to go up 4. Okay, and so tick marks, we'll just go by 2, say 2, 4, 6. Okay, and so I'm going to end up over here at 4. So question is, for what? Is it 4 coulombs? Because when I plot this, right, I got to have units on here. I'm going to lose -1 on this plot. Is it millicoulombs? So it's base units on this. This is amps. So therefore, that has to be coulombs. Is that the argument? Who thinks it should be millicoulombs? Anybody? No? All right, so let's say that this is 4 amps, okay? Then if I compute the slope, right here, sorry, 4 coulombs. If I compute the slope, then this is 4, right? How much is this?
1.
1 what?
Millisecond, 4.001.
So if this is 0, 0, 1, and that's 4, then what's that slope? 4 what? If this is 0, 0, 1, and that's 4, then the slope is 4,000 amps. Do I have 4,000 amps here? No. Okay, so that means that this probably ought to be what? This has got to be millicoulombs, right? It's got to be millicoulombs because the slope is the number 4, the actual number 4, right? So the rise over the run, if this is 001, then this has got to be 004. Now you could label the whole graph in base units and call this coulombs. This is kind of what you thought, right? Base units. That's fine, but then label this thing 001, 002, 003, put seconds there. Label this 002, 004, 006, and put coulombs here. That's correct also. But if I'm going to use numbers like 1, 2, 3 and put milliseconds, and I'm going to use 2, 4, 6 here, then this 2, 4, 6 is millicoulombs, right? Times 10 to the minus 3. You guys with me? It's a classic place for -1s on exam 2. Okay, figuring out what should be the actual units on this graph. Okay, all right, great. So I got the first one. So, man, do I even need this piece-by-piece analysis of every one? Let's do one more here. If I go 1 less than or equal to t less than or equal to 2 milliseconds, in the next interval, I of t equals what? Yeah, I of t is minus 2. That is a constant. And so that's the same as dq dt. So q of t is what kind of function? I of t is constant, right? Therefore, q of t would be linear, right, with a slope of what? Yeah, with the slope equal to -2. Right, so isn't it true that in just every single one of these, right, it's just going to be linear with the corresponding slope? Right, so over here, q of t slope -2. Right, over here, q of t slope, right, because this is dq dt, +2. Over here, q of t slope -4. Right, so we can think about that for every interval. We can figure that out. So if I finish off here, for the next 1 second, I got a slope of -2. This slope was 4, so the slope's not the same, right? So if I go over 1 second, and I have a slope of -2, where does that put me? It's -2 down from where I was, right? So I know where I left off. Okay, and that's going to put me here with a less steep slope. Okay, right there. So, can I just connect the rest of the dots based on this argument? So for the next 2 seconds, right, I'm going to be what? It's going to be a slope of 2 again, right? So for the next 2 seconds, over here, I got a slope of 2. How high will I go if I go over 2 and I got a slope of 2? I got to go up 4, right? So over 2, up 4, looks like it's going to put me up here at 6 at the end of 4, like that. So this slope is 2. This slope is -2. Okay, and then finally, where's the end point? I got a slope of -4, right? So in the last region, between 4 and 5, I go over 1. I got to go down -4. I'm currently at 6, so I'm going to end up where? Back at 2, right? Straight down like that. Okay, again, this guy now, slope -4. So what's the maximum charge? Yeah, Q max is 6. Units are millicoulombs. All right, so the point is, in each one of these intervals, this is constant, therefore Q is linear. The slope of that line is the value of the current. Questions on that? All right, so what about the next one? All right, the voltage, V of t. Okay, we talked about this a little bit in terms of what the strategy is. You get pretty much the action there from the Q, right? But then thinking about what the numbers would have to be, because it's basically just a scaling that happens here. All right, so if I go out the same, 1, 2, 3, 4, 5, time over here in milliseconds. Okay, then how does that thing scale, right, when I compute the voltage C dV dt? Okay, so if I of t, right, is equal to dq dt, which is equal to C dV dt, then if I want the dV dt, doesn't this mean that dV dt would be 1 over the C, right, times the dq dt? Right, so if this is Q of t, the dq dt is the slopes of each one of these. So I'm going to take the same plot, but the slope of every one of these lines is now multiplied by 1 over c. How much is c? 20 microfarads, right? 1 over 20 e minus 6 times dq dt. What's 1 over 20 e minus 6 equal to? Calculator, 1 over 20 e minus 6. Do we need a calculator for that?
Wait, why does it go from C to 1 over C?
So I'm solving for dv dt here, right? So by definition, I, which is dq dt, is equal to c dv dt. So what I'm doing here is solving for dv dt because I'm trying to plot v, and I want to know what is the slope of this graph. Right? I already know it's going to be lines. I just need to know the slope in each interval. You guys with me? So we solve for that. That puts a 1 over c here. So I got 1 over 20 e minus 6, which is how much? 50,000. Okay? So I got 50,000 times the dq dt. So thinking about if I have a plot of q, and at every place on the plot of v, the slope of v, okay, is 50,000 times, right? So the slope of v of t, okay, is 50,000 times the slope of q of t, right? Guys, in general, when you do a piece of math and you can see what it is, but you're not exactly sure how to interpret what it means, write the words out. Okay, when you write out the words, it helps say what it is, right? So this statement is, literally, this is the slope of v. It is equal to 50,000 times the slope of q, right? And write that out, and it gets your bearings. This is what I'm trying to do. So now, if I have this plot, and I want to redraw this plot where every line has a slope of 50,000 times these slopes, what is the plot going to look like? Yeah. The same exact plot with a different axis scale, right? To change the slope by 50,000, every y value gets changed by 50,000. Every x value stays the same. It's just scale on the y-axis. You guys with me? So that's it. So now if I scale the y-axis by 50,000, what are my tick marks going to be? So this tick mark is 2 what? 2 millicoulombs, which is really the same as how many coulombs? So this is 002, 004, 006, right? Stick with base units. So 002 times 50,000 is how much? 100, right? So don't I have 100, 200, 300, and the units on this are what? These are volts, right? Not millivolts. Okay, so think about what I have here. I have actual amps supplied. I have a capacitor measured in microfarads. The corresponding voltage is still volts that comes out, right? 100, 200, 300. The charge that's stored is millicoulombs. Okay, the voltage is actual volts. So that's it, right? I connect the same dots. I start at 0, all right? I go 2 tick marks up for here, right, like that, right? And then I go 1 tick mark down for here, and I go over 2 up to the top, right here, right? And then I go down 4 tick marks, which would put me here, okay? And then apparently the maximum voltage is what? Vmax equals 300 volts. Okay. Questions? Exam number 2 will have sketching problems. Usually, you'll see the posted exams. Usually, we'll have like one 20-point problem, and it'll basically be 4 things to sketch, 5 points each. We'll get a velocity and acceleration, and then a current and a voltage or a power. We'll mix it up. We'll have both dynamics kind of sketching and electricity on there. Okay, and we do that because real similar concept in terms of using slopes, right, to sketch the curves. But when you do the electrical problems, you really got to be cognizant about what are the units, right, getting the axis labels right, because this business of milliseconds, milliamps, millicoulombs, volts, getting that straight in electricity, pretty important, right, or you fry your component, okay, and or get killed. Questions? That's derivatives in electric circuits. Okay, and so we are going to move on. Last topic of derivatives. Derivatives in strength of materials. Anybody have any idea what strength of materials is? What does that even mean? Sometimes it's called mechanics of materials. Yes?
You gotta figure out how much will bend before it'll break.
Yeah, so basic things like how much can I bend something before it will break? Okay, and so, you know, a lot of times they'll call class in strength of materials. That's kind of the historical name for the class. More modern names sometimes are things like mechanics of deformable solids. It just sounds a little too exotic, right? It's not everything about the strength. Strength of a material is actually a material property, right? How strong is it? It's a property of the material. Strength of materials class, right? Whether you do it in like mechanical engineering, biomedical engineering, it's about how things deform under loads, right? And when they deform, thinking about stress and strain and how much stress it takes to break something, that's the thing that we're looking at. Okay, but not just break, right? If I am designing, I don't know, a microelectronic kind of sensor, right? Hard disk drives be obsolete within a couple of years. They almost are already, right? You buy laptops now with just flash storage and that's it. But hard disks, there's little devices, right, moving up and down, beams, little micro beams that are, you know, moving and deforming and vibrating and reading the magnetic media. Okay, and so we use mechanical devices all the time where it's not just is it going to break, but I want to know how to control the deformation. Right, so something actually deforms on purpose because it's part of the function. All right, springs, for example, they deform every time you use them. You use them over and over again, right? During regular use, the spring's not going to break, right? Could break over time and fatigue, okay? But the point is it's designed to be deformed and then to go back to its original size. Okay, so that's the idea. Strength of materials is all about how do things deform under loads. And a great topic for this class when we're talking about derivatives is the idea of deflection of beams, right? So this idea of how much can I bend a beam until it breaks, right? I can think about a beam as any kind of member that's got enough rigidity where it doesn't really deform under its own weight, okay? Although it can, there is some deformation here. But the idea is it can support, by virtue of its geometry, right, and material, it can support load on it now. And if I put load on it, it will deform, right? And so I can take this beam and I can bend it, and it'll be curved now, all right? And if I bend this thing enough, I can probably snap it in two. So this whole issue of design so it doesn't break, but clearly I could bend it, and then when I take the load off, it goes back to normal, right? And that's elastic deformation. So the whole idea of deforming things like beams, right, to understand how things deform when we design machines that have components that look like beams, artificial limbs, prosthetic devices that have long pieces of metal or carbon fiber or whatever, interested in the deformations and the forces that go on. Okay, so we can think about just this one topic and introduce some concepts, and then we realize with a few derivatives, we can answer all kinds of physical questions. Okay, so the topic of the day, and we'll carry into next time, is this idea of deflection of beams. Okay, and so the beam that I put up there, right, is a perfect example. Here's how we're going to look at this. If I have a beam and let's say, for example, it's attached to a wall. Okay, so on the left there, that's just meant to be a wall. I can apply a load to a beam in any number of ways. If it is a distributed load, like this, across the beam, I'm going to call that some load Q as a function of X. Okay, and so for example, this could be in pounds per inch. It's a distributed load, so the total load gets added up over the length, right? The other way to look at this would be newtons per meter. Okay, so that would be the units. Okay, and then the idea is this beam, much like we saw right here, right, when I grab this thing and I put load on it, it's going to deform. Right? And that actual deflection is one of the places in an engineering classroom where we use basically math lingo. Okay? The convention for this is typically this is the y-axis and this is the x-axis. Okay? And so we can think about the deformation of the beam. And when I say the deformation of the beam, what I really mean is just the center line that runs through it. Right? So in a problem like this, it's one-dimensional. Here it is straight, right? When I deform it, it's now in a deformed shape. And there's an equation for that curve. It's called the elastic curve of the beam, all right? Y of x. Okay, and so here's the idea. This thing loads up, and the beam, the center of the beam, will deform in some way. Okay, and so this deflection right here, okay, is y as a function of x. Okay, so literally, as this thing moves in the vertical plane, the new coordinates of every point along the length of the beam have a new y coordinate. That y as a function of x gives me the deformed shape of the beam. All right, it's the actual shape. So if that's the shape of the beam, okay, then at any given point on the beam, I can identify an angle that this thing makes. Okay? And that angle I'm going to call theta of x. Okay? Now, here's something kind of interesting to think about. Okay. When I do beam deflection theory, okay, I recognize that when I deform beams in practice, even when I have a deflection that I can see with the naked eye, okay, how big is that angle that's actually made, do you think? All right, I make this beam, let's say it's out of steel, I'm going to use it in some aluminum, whatever, use it in some mechanical application. Is that a big angle or a small angle? Right, I mean, if you think about it in radians, right, 1 radian is about how many degrees? Is 1 radian 180 degrees? How many radians does it take to go all the way around a circle? I like that answer, right? Usually 2 pi. We're trying to get numbers here. He said 6 point something. It takes about 6 to get all the way around a circle. So 1 is 1/6 of a circle. Pushing 60 degrees, right? 57 or something degrees. So, geez, 57 degrees is past 40. This is like 45. Okay, 57 is like way down here. Okay, that's not a small angle. That's 1 radian. I take, deflection of something like a hanging stoplight, right? Model that as a beam. That thing's got some deformation. It does something like that. Okay, that angle is a lot less than 1. Okay, in terms of radians. Okay, so here's something interesting. Pull out your calculator. And we may have talked about this a little already. Right, and let's say I got an angle now that's, I don't know, if 1 radian is 50 something degrees, let's say it's 1/10 of that. It's like 5 degrees, right? So take 5 degrees, right, and convert that to radians. What would you get? 5 degrees. What is it? Okay, so give me a decimal. So 5. 0.087. All right, now. .087 radians, okay? Take the tangent of that. Make sure your calculator's in radian mode. What do you get? Is your calculator broken? What did you just say?
0.087.
So the angle's 0.087, and he took the tangent of the angle and he got what? 0.087. That's interesting. By the way, what's the tangent of this? This is the theta we're talking about, right? By definition, tangent is what? Opposite over adjacent. If this is the tangent line, right, then the slope of the tangent line is also what? Is it not the derivative? If this is 1, then the vertical is dy dx, right? Which is equal to the tangent of theta, no matter how big theta is. But for typical thetas with small angles, this is basically the same as the theta. You just did the number, right? Even 5 degrees, I can see with the naked eye that deformation. To 3 digits, I get the same answer for theta and tan theta. Okay, so the reason I make this point is this theta of x, the slope of the beam at any given point as an angle in radians, is actually just the derivative, dy dx. Okay, so this is true for small angles, right? In other words, theta much less than 1, right? And of course, 1 is the dimensionless measure of an angle, radians. Okay, so if theta is much less than 1, this is true. dy dx is the theta. Okay, so immediately, I know that if I have y of x, right, that theta of x is the slope right away, right? So theta of x is equal to dy dx for small angles, okay, and that is the slope of y of x, right? Slope of y of x, and that's measured in radians. So right away, if I'm thinking about a mechanical device, for example, like in a plant, right, they use things like shafts to transmit power. And when I design a shaft system and I want to transmit power from gears and things, I've got to design the whole thing and lay it out, and the shaft rotates, and we use things called bearings, right? It rotates into bearings to make it rotate smoothly. And a deformation of that shaft, because it has loads on it, we can use beam deflection theory for that. And I'm worried about things like how much the angle changes, right? Not just the deflection itself, because this thing's got to fit. It's got to rotate nice in the bearings. If I get too much slope at the bearings, then I can damage the bearings themselves, right? So all these kind of things are important, right? So I'm interested in the deformation itself. I'm interested in the slope of the deformation at certain points, okay? And then here's a flash forward to some things that you'll get a little bit maybe in statics, but then definitely again in strength of materials. Turns out that I can get the internal forces, okay, inside the beam in terms of derivatives. Okay, so here's the thing. Let me take a little section of this beam and think about, what are the forces inside? So this is any length here, right, where I've got the Q of x, okay, applied to a piece of the beam. If this beam is under equilibrium, that can't be the only load on the beam. Right? Because if it's the only load, then the load is clearly not balanced. Right? This thing's accelerating downward. So in order for this beam to be in equilibrium in a deformed configuration like this, right, the loads everywhere on this beam have to be balanced. So I could take any section of the beam, and whatever's going on the inside needs to balance whatever's going on the outside, or it won't be in equilibrium. So I can take a section like this, and I could say, well, what would I have in here? Okay, I could have a combination of forces up and down, transverse to the beam. Those are called shear forces. Okay, and then the other thing I could have, if this beam is going to be bent, okay, into a shape like this, okay, is I can have what's called bending moments in the beam, okay, which is the idea of force multiplied by distance, right? In high school physics, they call these torques. Okay, in mechanics and materials, we don't call those torques. Torques, for us in engineering, are twisting moments like this, right, when I twist something. So we'll talk a little more about twisting next time, give you a homework problem on that. So this isn't twisting, this is bending things into a circle. So I can have internal things that look like this. So a shear force V, a bending moment M, okay? So, why am I telling you all of this? All right, we're learning derivatives here today. Okay, it turns out that when you do the derivations for the forces that have to balance a beam like this, okay, you will discover the following, that the moment M, okay, is a beam property, okay, and in fact, the property here, okay, I'm going to call it EI. I'll define what that is in a minute, okay, but I've got EI, a geometric and material property of the beam, okay, times 2 derivatives of y with respect to x. Okay, so this is called the moment inside the beam. Okay, units on that are force times distance, so it's pounds times inches or newtons times meter. So I've got that. So think about it. I started with y of x. If I take one derivative, I get the slope, right? dy dx. If I take the derivative again, and I multiply by a property of the beam, okay, I get the internal moment in the beam. Okay, well, it turns out that v of x is actually the derivative of the moment, dm dx. Okay, and if that's true, then the EI is still out front, because that's a constant property of the beam. And I have another derivative. So look at this one. 3 derivatives of y with respect to x. And then finally, very interesting, these internal loads have to balance the external. And the way this works out is that the q turns out to be minus the derivative of the v, dv dx. Okay, and so what I'm going to get here is minus the EI times one more derivative, 4 derivatives y with respect to x. Okay, and so the units on each of these, V is the shear force, right? This is the shear force. And so the units of force would be either pounds or newtons, right? And then finally Q is one more derivative, right? So force per unit length. And that's how I get distributed load. So this is the load, again, pounds per inch or Newton per meter. Okay, and so what's the punchline to all of this? For a beam deformation problem, if I have an equation for the elastic curve, which in this class, we're just going to give you the equation, okay, then if I just start taking derivatives, I can understand everything I want to know about how the beam deforms, and also whether or not it might break, right? Because one derivative gives me the slope, helps me sketch the deformation. Another derivative, multiplied by this EI here, okay, gives me the moment. And it also tells me something about the shape of the deformation. What does a second derivative tell you when you're sketching a function? Say what? Inflection points, you can get that from it, but in general, second derivative is a measure of what? Change in the rate of change, which we call what? I can use it for max and mins. It's the concavity. Concave up, concave down, right? So the moment, look, I mean, why does this work? If I want to bend a beam, how do I bend a beam, right? I got to put it between my two fingers. They're a distance apart from one another, and exert force times distance, right? When I do force times distance, I get bending. What's the shape of this thing? Yeah, it's a concave down, smooth curve, right? And so it makes sense, right, that the second derivative, the bending, is the concavity, but I got this EI in here. Okay, and so finally, I guess the one thing I will define for you is the EI. This is called the flexural rigidity of the beam. Okay, of the beam. This is in pounds times square inches. Fix that, pounds times inches squared, or newtons times meters squared, okay, would be the units for that. Okay, and each of these things is a different property, right? So E is called the elastic modulus. That is a property of the material itself, okay? And that is measured in either pounds per square inch or newtons per square meter, okay? And finally, I is actually something, if you've had calculus, you may have seen before. This is the second moment of inertia, also called moment of area. Okay, and if you've had some calculus, turns out the definition of I is in terms of an integral. Okay, and so we'll talk maybe a little more about that later. Inches to the fourth or meters to the fourth. Okay, so here's the thing. The I has to do with basically how beefy the cross section is. So for example, if I go to bend this beam, this is a flimsy beam. Right? And so I put a load on it and it bends an awful lot, not very resistant. Okay? Now look, this is the exact same beam. If I flip it 90 degrees like this and I try and bend it this way, heck of a lot harder. Right? This is the reason why you look at beams for buildings, for example. They have a flange and a big web, right? I-beams. They're tall. Hard to bend things about the tall axis, right? As hard as I'm trying to bend this thing's not bending at all. If I flip it this way, now it bends. Okay, so easy to bend about the thin direction, really hard to bend about the thick direction. Okay, and so this I is a property of the cross section. It's got to do with the orientation of the beam relative to the loads and the geometry. Okay, the E is whether or not this beam is made out of plastic, like this one, relatively small e, or it could be made out of steel, right? This exact same beam, same exact geometry made out of steel would be harder or easier to bend. Harder. A lot harder to bend, okay? So it's a stiffer material, much bigger E. Okay, and that's the idea. So when I design a beam, I got all these options. I got the geometry of the cross section, I've got the length of the beam, I've got the way the loads are applied, the way it's supported, but the crux of it is, if I can take 4 derivatives in a row, okay, then I can answer pretty much everything I need to know about a beam. All right, here's the other beauty of this. Most real beam problems with real loads, right, like the one that we're doing right here, whether I take it and I put moments on the end, or whether I hold it at one end and I put a point load on the end, turns out the deflection curve, you tell me, what kind of function do you think this is? Or the squared. So what kind of function is a squared? Parabola, right? In general, polynomials are common solutions for beam deflection. Okay, and polynomials, really easy to take the derivative, right? It's like the t to the n's, except in this case, we're dealing with x, not with t. Okay? All right, so all of this background, okay, can we now solve some problems? I'm going to leave the picture on the left with the basic definitions. Get rid of the force stuff for now. Okay, and let's just do some examples. The beauty of these beam problems, which is generally a little bit uncomfortable for first-year students, is that they've got parameters all over them. Right? Most of these beam problems, there's no number, right, that you're going to get, like a decimal, for the answer. Okay? So it's going to have a whole bunch of letters. E and I and the length of the beam and a load P, right? And the beauty of that is when we solve problems in engineering design, we actually want answers in terms of letters more often than answers in terms of numbers, because then we get to change the letters, right, and have a different design. Right?
Use different formulas.
Well, same formula, but different values of the letters, right? So in other words, what happens when I double the length of the beam? What happens if I switch the material from aluminum to steel? Those kind of questions. If we have answers with parameters, we can do that. All right, so let's look for example. This is a problem right out of ME 3120. Also, if you're a BME 3430. Okay, and this would be a cantilever with an end load. So this is one of the most classic problems in all of mechanics of materials, okay, and it represents an awful lot of physical situations. Okay, it's the one I was doing right here that said, look, what if I come with a beam and I just put a load on the end? So this is Y, this is X. Just to be clear, the intersection of Y and X, right, is X equals 0 over here at the wall. Right? I'm not drawing the axis through the beam, I'm showing the axis here, but the 0 point is right there. Okay? So if this is the load, what are my parameters? The length of the beam, L, is one parameter. Okay? And the beam's got property EI associated with it. So, with the beam. Okay? And this is a load P over here at the end. And the beam is going to deform in some way like this. So this is the equation of the deflection curve, y of x. So it turns out, in strength of materials, you can solve for this deflection curve, and the answer is the following. It is P divided by 6EI, okay, times a polynomial, x cubed minus 3L x squared. Okay, and let's just say that we're working in meters, okay, but in fact, normally, when you have parameters built into an equation, Okay, you don't have to put the units because the units are contained in the parameters, right? So whether this is inches or, meters, well, that'll depend on what I put in for the P and the E and the I. But I got to have self-consistent units. All right, so what would I like to find? Okay, I want to find the deflection and the slope at the free end. So deflection and slope, okay, at the free end, which is x equals L, right? So if I have y as a function of x equals L is the value of the deflection all the way at the end there, right? What is y evaluated at L? So first part, deflection. If I'm given the deflection curve y of x, and I want to find the deflection at x equals L, do I need derivatives for that? So this is the equation, right, that defines the shape of this curve, okay? Y is a function of x, and I want to know what's the value of the deflection at x equals L. What do I do? Suggestions. Substitute L for x. That's it. Okay, so the first physical question we're going to answer, there's no calculus here. This is a piece of algebra. Let's plug in the L and see what we get. So for the deflection, I need y evaluated at L, not multiplied by L, evaluated at L. Plug in an L for the x. So I still have P over 6EI out front. And I've got x cubed, so that's going to be L cubed minus 3L times, I plug in an L for the x, L squared. What's L times L squared?
L3.
L what?
The cube.
L cubed. Okay, so y at L, right, is, I got P over 6EI. And so I got L cubed minus 3L cubed, which is what? What's L cubed minus 3L cubed? Negative 2 L cubed, right? All right, and so can I simplify this anymore? I can multiply it, so what do I get? Negative 2PL cubed divided by 6EI. Can I simplify that? The 2 and a 6, right? So I get minus PL cubed divided by what? 3EI. Okay. So when I put a load P on the end of a beam, the deflection is PL cubed over 3EI. That's the same statement as saying the stiffness of that beam, like a spring, right? F equals K times X. The F is the P. The X is the deflection. The stiffness is 3EI divided by L cubed. Right? So that relates how much I deform relative to the load. So for example, if I want this thing to deform half as much, right? What's a better thing to adjust? The material, right? Try and get a new material. If I want it to be half as much, then the E value would be how much bigger? Twice as big. So I need to find a material with twice the stiffness. That'll take care of it. I put a 2E down here. I'll get half the value. Or I could change the length. What do I get more bang for the buck out of? Yeah, if I cut the length in half, how much less is the deflection?
Double.
You get one answer for double, one answer for half. Again, this is why we do problems with letters in them, right? Because once I have this answer, it's the answer for any beam with a load on the end. any material, any length, any cross-section, this is the answer. So if I cut the length in half, how much does the deflection change? Say again?
By an eighth.
By an eighth. 8 times less deflection. Replace L with L over 2. You got to cube it, right? So it's 1/2 cubed. It's a factor of 8. So clearly this thing's way more sensitive to the length than it is to the material, right? So you make a beam really long, it gets awful flimsy, no matter what it's made out of. That's an interesting result, right? Steel beam that's long enough, I can bend it with my fingertip. Okay. All right, so good. So that's the deflection. What about the slope? And incidentally, the slope we want is right here at the end, right? So if I came right there at the end, this is theta evaluated at L, right? This actual value, this distance right here, this is y evaluated at L. That's what we're getting. Okay, and so if I want the slope, then how do I calculate the slope if I have the deflection curve? Yeah, I got y of x, right? I ought to be able to take the derivative. So theta of x is dy dx, so I need the derivative with respect to x of the deflection curve. Deflection is p over 6ei, right? And I got x cubed minus 3lx squared. So I need that derivative. Somebody help me out. Theta of x. What do I do with that p over 6ei out in front there? Yeah, that's not a function of x, right? These are numbers. Their parameters are the problem. The p could be 100 pounds, right? The e could be 30 times 10 to the 6th. The I, whatever, 0.25 inches to the 4th. Okay? So it could be in whatever those numbers are. So I put p divided by 6ei out in front, and now I need the derivative of these terms here. So, even if you never had calculus, right? I've got terms taking derivative with respect to x, not time, right? So I need x, not time here. But thinking about that, then what type of function are we using off the sheet here? Yeah, it's like t to the n, but it's x to the n. Okay, and in fact, if you turn the sheet around, the math department likes to have all of their formulas in terms of x, right? So this is the derivative of the x to the n type rule. Okay, so same thing, right? Derivative of x cubed would give me what? 3x squared. The 3 comes down, x to 1 less power. So I get 3x squared. And then I got 3l times x squared. What do I do with this 3l? It's a constant, right? So I put minus 3l. Now I need the derivative of x squared. Just 2x, right? So again, if you can do that in your head in one step, that is fine. Okay, I just wrote it out there so we'd be clear what we got. Okay, and so then now I should be able to simplify the algebra a little bit. So I've got p over 6ei. Right. Theta of x is p over 6ei, okay, times, I've got 3x squared minus 2 times 3 is 6lx. Excellent. So the question was, what's the deflection at x equals L? What's the slope at x equals L? This gives me the slope at any value of x. If I want the slope at x equals L, what do? And I plug in L, right? So at x equals L, I want to evaluate theta of L, not theta times L, theta of L, right? And we'll plug in an L, I'll get p over 6ei. And then I'll have 3, plug in an L for x, 3l squared, minus 6l times L, that's 6l squared. You know, the other beauty of these problems with letters is that when I'm doing a physical quantity and I got to add up terms, the units had better square away, right? In other words, if this was 3l squared and I wrote minus 6l here, I would know that I made a mistake, Okay, because the letters have to add up. If I got L squared there, I better have L squared there. Okay, so what's 3L squared minus 6L squared? Negative 3L squared. So theta of L minus 3L squared. So P over 6EI. Negative 3L squared. Can I simplify that anymore? So the 3 into the 6 goes twice, right? So I get minus PL squared over what? 2EI. Incidentally, why do I have negative numbers for the deflection and the slope here? Yeah, because y is positive up by virtue of how I define this problem. Okay, if I would have said y was positive down, then the deflection curve would have a negative right here, and then these would have been positive numbers. Okay, so just the way the problem is set up. All right, so the deflection is down, that passes a sanity check. The slope is a negative slope, that passes the sanity check. Okay, let me ask you this. What's more sensitive to the length of the beam? The deflection or the slope?
Deflection.
Yeah, so if I double the length of the beam, the deflection changes by how much? If I double the length, deflection changes by 8 times, right? I put a 2L. How much does the slope change? 4 times. I put a 2L here, right? And I get 4. So the point is, again, you get a sense of what is more sensitive, right? Deflection or slope to changes in the parameters. What if I make the material twice as stiff? 3 times as stiff. I go from aluminum to steel. That's a factor of 3 roughly. Deflection changes by how much? I go from aluminum to steel. 3 times stiffer. Deflection changes by? Is it? So the material is what one of these letters here? It's the E value. So if the E value is 3 times bigger, then the deflection is what? Is it a 1/9 less? It's just a 1/3, right? I replace the E with the 3E and I get 1/3. What about the slope? Replace the E with 3E and get what? It's still 1/3, right? So the slope's not always more sensitive to a design change than the deflection. If I change the length, I get way more effect on deflection than I do slope. If I change the material, I get the same effect. Right? This is why we do problems with letters, okay? So we can get a sense for how can I change the design? I'm the engineer, right? And so I can get it to do what I want for whatever parameter I'm interested in by adjusting how I design the beam, okay? Great. Questions on this? All right, so we got, I don't know, 4 pages of lecture notes to dig into some more cool beam physics. I can bang that out in one lecture, okay? So unprecedented, what? A 5-minute early release from EGR 1010. Okay, anybody with questions, catch me up front. Otherwise, we're done.